Professor Emeritus in Keller. He's professor in computer engineering, also in electrical engineering. He has held a wide variety of positions at IEEE, and he works with academia and also with industry. And since somebody else already made an introduction yesterday, I'm going to give it short. Thank you.
Cortado. So here's the young Claudio and Pablo Pablo Uno. And all of these, most of these pictures were from 2007, when we were here for a summer school in Santiago. And this is, of course, your observatory in Lodo. And there's one picture here that's not from Chile, and that's this one right here. This is from Lisbon, when Pablo and I went down to get the Jiu-Jitsu or some, whatever that little cherry brandy stuff is that they like so much. So before I start, somebody asked me yesterday the difference between what my streaming clustering approach and DB-scan. And it turned out, I went blank, which I do a lot these days, just kind of nothing in the head, goes out. And it's the difference is that DB-scan's not a streaming clustering algorithm. It's a density-based algorithm, but you have to have all the data. So at best, it's a batch mode. But there is an instantiation of that called DenStream, which we don't quite understand yet, but we're going to compare to in the past. So anyway, I just want to clear that up. So yesterday we talked about using fuzzy and possibilistic memberships in the clustering problem, and both Jim and I did. And today I'm going to talk about more other kinds of fuzzy set theory. So I have a little fuzzy set intro in here and fuzzy logic intro in here. But this is about something called recognition technology that I, that sort of is an application area. And it was a vision of Lotfi-Zadeh, the creator of fuzzy sets. And so this is a big interdisciplinary group. We have the Center for Elder Care and Rehabilitation Technology at the University of Missouri. This is the website for it. There are a billion papers out there and projects and whatnot. And also, I'm going to talk about something about explosive hazard detection, landmines. And so I've gotten lots of funding over the years for that. And so this is, it's sort of where advanced sensing meets data science. This is actually, I was pandering to somebody one time, I was talking about this, who was in a data science program. And so I thought, oh, well, I should call it data science. I don't even know what that means, but it could be, But it's my tribute to Lotfi, the creator of fuzzy sets, and these are a couple of early pictures. Look at the hair on this guy, man, I tell you. But anyway, there's a nice picture of Zadeh, and I like it because I'm a pixel up in his brain, so I figure that must mean something, to somebody, So, what is recognition technology? So it was defined by Lotfi as, and he said it this way, he said it's current or future system, this back in the mid-1990s, right, that are going to provide a quantum jump in capabilities of recognition, right, of things that we do for recognition. Whoop. And so he said it's a result, it's going to happen because of three convergent rivers. You have at least two rivers. I was at the join of two of them the other day. Major advances in sensing technology. He said, hey, sensors are going to keep getting better and cheaper. Major advances in data processing technology, the ability to take the sensors and do something with the data, particularly in a real-time environment. And the use, of course, he created fuzzy set theory. So so he said it's the use of soft computing, which is a little broader than fuzzy sets. He'd include all neural network activity and all probabilistic reasoning inside soft computing, right? As opposed to the making crisp decisions all the time, to infer conclusions. So he wrote a paper for Anchorage. This is the only time I saw Lotfi ever give a 20-minute talk, you know, because usually he was giving plenary talks all the time, you know, and so I got him to give a 20-minute talk on this in Anchorage. So the question, you know, that I'm going to pose is, was Lotfi right? Was there a quantum leap from 1996 or 7 when he first started talking about this till now? And I'm going to look at it from two different perspectives. One is, and these are very different, one is explosive hazard detection, because I have a lot of experience with trying to find things that blow up, that are either buried in the ground or sitting on top of the ground or under the water, you know, and also this elder care, which is misspelled. Elder care. I'm going to look at it from these three pillars of recognition technology, both from a research standpoint, because of course that's what I like to do, and from product deployment, which is why this stuff might work, right? So here's the outline there, and again, too bad Sanaz too bad she had to leave. She was like, you know, like, oh, I have to leave, I'm sorry. But for years, this is a reinforcement learning example, right? Because for years, I used black and gold in my slides interchangeably, because the University of Missouri colors are black and gold. I mean, I got them on my socks, you know, they're everywhere, right? And Jim told me, every time he saw the slide, he said, that yellow stuff you got up there, you can't read. Right? And I kept saying, yeah. And he told me over and over and over again. And so finally, you know, there was another guy who does research in color who said, yeah, Jim's right. You can't see this. You know, it's like almost invisible when you put the yellow stuff on the white background. And so finally, you know, I just had to admit it. So the idea here is that this is the outline, but it's the black thing that we're going to talk about. So pretend like this is invisible. Right? If you can't see it, pretend it's invisible. If you can't see it, I've done my job. Right? So this was my first picture with Lotfi. Back, I don't know, 1991, I think, 90, something like that. We both looked fresh-faced and excited. And so the two problem domains are explosive hazard detection and elder care, which is spelled correctly now. They're very different scale problems, right? And they have very different purposes, obviously. They both produce lots of data, mountains of data, sensor data, and they share, in my opinion, these pillars of the recognition technology idea. And this was my last picture with Lotfi, you know, like the year before he passed away. We had a deal in Berkeley. He was 96 years old. And he still gave a talk, you know. Okay, so here's the laboratory, in a sense, for the elder care. So I'm going to jump back and forth a lot, right, which is the way my brain works anyway. I can't keep focused on anything. And so I'm going to go back and forth between these two problem domains. So this is the laboratory for elder care. It's an apartment complex built by a company, right? But designed by the School of Nursing, right? At the University of Missouri, and of course it's called. Everything is a Tiger, you know, in Missouri. So this is called Tiger Place. It's got but it was designed as a laboratory. So it's got the right kind of power. It's got really great internet connectivity, unlike some places, and it's, and so we use it, and the people that are at this facility, it's something called aging in place. So the goal is you move in there while you're still capable, while you still are mobile and you know, functionally active, and you die there, right? In other words, the standard model for elder care is you go into a retirement facility, and then when something happens to you and you need more care, they move you into another place, right, where they can concentrate care. Right, so they have more nurses and doctors available, and then something else happens, and you go into a you know, very high-skilled nursing facility, and then you go into a hospice, you know, before you pass away. And each time you move, it becomes more sterile. You know, it becomes more like a hospital room instead of your apartment with your stuff, right? And so the idea here, they had changed the law in the state to do this, but the idea here is that when you need more care, it comes to you, as opposed to you being moved to there. Now, it's a little more expensive because of that, because, you know, they have to pay for the care coming in, but overall, it's saving a lot of money, particularly to the insurance companies that are footing a lot of the bill, because your quality of life is better, and hence you're more likely to not need as much skilled nursing care because you have a better life going on. Besides the fact that your mental state is so much better. Okay, so now here's explosive hazard detection. This is the laboratory, you know, places like this, right? Looking for things that look like this, or here they are here, you know. This is infrared, you know, this is acoustic. I'll get to that in a minute. This is looking under the ground with a radar. Right? This is in the forward direction. This is the straight down. You know. And so we're going to first talk about the advances in sensing technology. So here's forward-looking explosive. This is the typical kind of research vehicle that's in there that uses many different electro-optics, IR cameras. You have lots of video stream data. You know, I mean, sometimes it's really good. You can look at the ground and you can just say, oh, it looks like there's like headlights sitting in the ground where something's buried, you know. And other times you look and it's just, it looks, you can't see it, same place, different time of day, you know. But anyway, there's lots of different sensors mounted on here, and of course you've got the GPR. Right. Here's ground penetrating radar, forward looking. So you got all these radar antennas mounted on a vehicle, right? And they're looking out. And of course the problem with that is when they're looking out, the radar signal goes out, hits the ground, and of course where does most of it end up? Out that way, right? You know, bounces off. But some of it goes into the ground, right? Comes back out and comes back, reflected back. If there's an object either on the ground or under the ground, you get a return signal, right? And so, you know, it's a very complicated signal processing problem, but that's the idea, is that they, and, you know, and of course all the sensor people all build all these things, you know, the perfect sensor in there. And of course there is no such thing, right? This is a newer system. This is a three-dimensional radar. So this builds a three-dimensional representation of what it's looking at. This is actually looking off to the side. You're driving this way, it's looking off over here. And so these are three representations. You know, one of them is, what do you see from this is projections, right? What do you see from the side? The top one is, what would you see if you were above it, looking straight down, right? Because it builds a whole volume of data right in here. And this third one, this thing right here, is, they call it the dog view. Because, you know, when you're driving, if you have a dog and you're driving with the dog sticks its head out, you know, looks out like this. So this is more like a giraffe. You know, if you look out this way and then turn your head, it's what you would see that direction, right? So these are just three orthogonal projections of a three-dimensional data cube in there. And, you know, it's of course a huge sensor. I mean, big. You know, this thing's big. Right? This is a acoustic sensor, very much like sonar. You know, this is very cheap. This thing is very cheap. It's got a speaker that emits a chirp. You know, beep, beep. Right? And then when that sound wave hits something, it'll bounce back. Right? And then you can get a whole bunch of returns on this thing, and then you have to make sense out of that somehow. Right? And so it's like sonar in that sense. It's an active sensor, right? Because it sends out, well, a lot of these are active. I mean, the radars are clearly active, right? Because you're emitting a signal. And so it's only the video, the infrared or the visible camera systems that are passive, right? That you can look and not expose yourself to this. But, you know, so now, of course, what have they done? They've decided, oh, maybe I should put like 16 microphones and or maybe one microphone and 16 receivers. 16, right? One speaker, 16 microphones, right? So that you can get a broader view of this. You can build synthetic apertures out of this. So anyway, this is just a little simple device in here. And of course, what are we doing now? Sanaz talked about this earlier, is, you know, with the drones and that. Now the idea is, if you've got something that's hard to find, I mean, first of all, in this particular problem domain, you don't really want to get too close to the objects that you're trying to find, because they blow up. Right? And you're trying to save lives by finding them before they do what they were designed to do. So the idea now is that we can deliver the sensor to the object, right? So if you're having a hard time with something like inside of a bush, you might be able to see it better if you were behind rather than in front. So driving down the road. So rather than, you know, rely on your ability to find a thing from the front, you just go around the back. So you send a sensor around the back. And of course, all the problems that you talked about with the robot swarms and all that, this all applies now, is that we have to be really careful, you know, about tasking and, you know, making sure that we don't run into each other, and, you know, because it's true, when you start flying these things, the first thing they do is go like this, BAM! And hit the ground, you know. So we've had, but these aren't nearly as expensive as the Airbus example she was talking about. I mean, these are a couple of orders of magnitude cheaper. You know, these are not, I mean, they're pretty heavy duty, but they're not that expensive. Okay, so that's a bunch of sensors for finding stuff that blows up, right? Over here, it's much more individualized. I mentioned this yesterday to somebody who asked a question. Much more individualized. The sensors that we have here are deployed in each apartment, each person's apartment, and I'll show you some of these in a little bit. And the idea here is that somehow we collect a bunch of sensor data, we're going to integrate it, and, you know, this is the kind of picture you put into a proposal to get money, right? That's what this is for. Because it's like the big picture, you know, kind of thing. And of course, you have the happy elder over here and the happy nurse, right? You know, what could be better? Take care of old people and babies. You can't miss on that. All right, so here's some of the sensors here. Just motion sensors, a lot of motion sensors in here, over the shower, in the various rooms in the apartment, you know, detecting very coarse movement. Right, with the motion sensors. There's a bed sensor. I'll show you another picture of the bed sensor a little bit that goes under the mattress in here that measures sleep patterns. So we're really getting a lot of information out of what's going on while the person is asleep. And we can get pulse and respiration rate. You know, for example, we had the psychiatric department at the hospital wanted to monitor the people in the psych ward to make sure they're still alive. you know, that they didn't do something to hurt themselves. And so being able to detect breathing is important. You know, even, I mean, a simple example like that, you know, because they can't go in every time, right? Should have had this in Jerry Epstein's cell. And then video of some kind, right? This is actually a Kinect, an Xbox Kinect that we started using, but that produces depth images, right? Images of distance in there. So here is the depth. We used to use webcams. We started out with webcams, and we would put a camera, say, on that wall and one on this wall. I'll show you some pictures of that in a little bit, some video. And then we would collect images in both of these projection spaces and then try to rebuild the three-dimensional representation out there. And about the time we got really good at doing that, the Xbox came out. And so, you know, the Kinect already does it sort of for you. And so we kind of lost, you know, we just said, okay, never mind. Never mind trying to calibrate these two independent cameras. But what we did is, over the refrigerator, we installed cabinets, because no old person wants to go up over the refrigerator to put dishes or something, you know, up there. So this was blank. So we installed a cabinet over the refrigerator and stuck the computers inside there. And when we used the webcams, we had to have really heavy-duty computers because we were doing a lot of image processing with it. And so with GPU cards and, you know, all kinds of stuff like that. And so they got really hot in there, especially when you close the thing, right? So we tried drilling holes in the bottom to get some air flow, you know, going in. But we smoked these things, you know, we just burned the computers up. The nice thing is that the connected depth cameras, now that do most of the work for us, you can use a much smaller computer because the work is already done inside the box. And the box looks a lot different nowadays than the original Kinect. But anyway, so this cabinet is now essentially empty. I mean, it's got a little tiny little thing about this big stuck in there. You know, we tried putting fans. You know, that would be a nice way to cool something down, put fans. But then the people would say, ooh, it's so noisy. You know, and I mean, this is where they live. So we said, okay, we'll start doing that. Oh, we put radar. We have radar looking down like this, right, for landmine. This is a radar system that's looking out. You put it by the door, right, the doorway. And so when people walk towards the door, you can measure, it's a Doppler thing, just like the weather radars. And so you can measure how fast they're walking, and you can measure their gait patterns, right, which is a very important parameter for older people. So this is the bed sensor, right? And this is why I'm saying it's a very different scale from the landmine detection, is that this is a tube of water. Right? It's a sealed tube, that's why it's called a hydraulic sensor. Right? It's a sealed tube of water with a pressure sensor on the end. Now we put 4 of them here, so that, you know, it depends on where you're laying on a bed. If you're rolling around on a bed, you want to make sure that one of these tubes of water is underneath where your heart and lungs are, and you put the mattress on top of this. So this is under the mattress, so there's no. It's all passive, right? There's no, you don't have to wear something. I mean, sure, it'd be a lot easier if we all wore, you know, a little Woody watch, you know, with accelerometers on it. But the nurses told us, the nursing professors told us that elders don't want to wear stuff. You know, you can't force them to wear a watch or a pendant or some, you know, a little thing around their neck, kind of thing, you know, like a lanyard. You know, put that around their neck, because A, they don't like to do it, and second, they'll forget to charge it. You know, they just won't charge it, and so then it goes dead, and then you think, oh my gosh, are they dead? You know, because the sensor stopped working. So this is kind of what the signal looks like in the best of all possible worlds, right here. You get this really high amplitude, low frequency carrier signal, and that's your breathing, right? So, like that, you know, of course, then if it goes, you know, then you know something's wrong, right? And so you can filter that out without any trouble. And then the thing that's superimposed on top of it is actually a signal that represents the change of mass of the blood during the cardiac cycle. So when the heart pumps, goes up the aorta, right, out of the aorta, down your back, you know, and up to your brain, hopefully, and you know, and so the mass of the blood changes, and that goes out to the extremities, collects back up in the venous system, right, in the vein, and goes back into the heart. And so the mass change, I always thought it was the motion, you know, like that, but it's actually the change of mass of the blood. And you get this signal that's called a ballistocardiogram, right? And it's been known for many years. They just never had a good way to measure it, right? And so this is our version of it. And it's a little different than the ECG, you know, when you put the leads on your chest, right? Because that's measuring the electrical activity of the heart. So the ballistocardiogram is always sort of staged off of where the electrocardiogram is at, because the electrocardiogram is sending signals to the heart saying, go for it. No, it's not sending signals, I mean, it's detecting the electrical signals that say, okay, it's time to pump, you know, kind of thing. And then you get the pump, and you get the blood flow, right? So it's a different looking signal. Of course, they label the peaks differently in here, but it's been known for a long time. It's a very noisy signal. So if you roll around, you know, you don't get good readings. You know, this is somebody laying very, very still on the bed, right? On their back. Right? You roll on your side, you side sleeper, you know, and you want this to work, you should lay on your left side, because, you know, so the heart's closer to the sensors. Okay, thermal would be great. You know, back when we started doing this in 2005, I think, was when we first started putting these sensors in people's apartment. Trying to buy a thermal sensor was tens of thousands of dollars. You know, and we're talking about things we want the sensors to cost $100 at most. Right? You don't want to spend a lot of money on the sensor, because I have to put sensors in everybody's apartment. Right? So, of course, what happened a couple of years ago? You know, that little thing you stick onto your, you know, stick at the bottom of the iPhone. It's a FLIR camera. You know, and so now what's happened is that technology right there that'll produce a heat map, right, an actual heat map, is now really inexpensive, and it's built into the new version of the depth sensors. So that box, that Connect box, now the new depth sensors all have an IR camera stuck on there. I'll show you why that's important in a little bit. And so this is kind of like the Internet of Things. You know what? The light bulbs can start telling us stuff. You know, if you wire up the room right. Okay, so now the second pillar is signal processing, sensor processing. And of course, gee, I mean, you know, we now have small computers that have huge capabilities. You know, and when GPUs came out, and people realized that you don't have to just do graphics with a graphics processing unit. You can use them as a general purpose engine. Right, things just opened up greatly. And so these are just some random pictures of processing that huge amount of data. This is from the forward-looking ground-penetrating radar. Because what happens is you send these signals out, some of them bounce back, and you've got a whole bunch of receivers, antenna, right? Collecting all this data, and it's all time data. And so what you have to do is you have to figure out, at this spot in the ground right there, where should the signals that come back at me, where should they be in this whole mess of stuff coming back? You have to do that for every spot in the ground that you're interested in, right? And so that's a huge processing problem, you know, but now, I mean, nobody even thinks of it. You just do it. You know, you just say some graduate student, here's, you know, 87 gigabytes of raw sensor data. Here, just go produce these images for me. You know, maybe it's tomorrow that you get them, but it's not like, you know, 8 months from now kind of thing. And they can actually get a lot of this right on the fly because, of course, this is real-time decision making because you don't want to drive over something that might blow up, right? You do want to see it. This is processing that three-dimensional cube of data, right? You know, so I had a graduate student who's now got his PhD and is at a university. You know, I said, hey, how can we look at this cube of data that, you know, represents this radar cross-section of this? And he came up with this idea of looking at it at different threshold levels and building ISO curves, you know, and ISO surfaces. And so this is just to show, and these are huge processing problems that when I was in school or when I was an assistant professor, we'd have never even conceived of a problem like this, you know, because as Jim pointed out, we had to punch a card deck and stick it in, you know, overnight kind of thing. You know, or here's a LiDAR, right, a range. This is a gigantic point cloud of data. Right? It just gives you, again, distance based on visible, right? It's a laser rangefinder, essentially, at every point, and it builds these things. And so, you know, my student just said, hey, you know, it'd look a lot more 3D-ish if I just wiggled it, you know? And so he produced these things called a wigglegram, right? And there's some objects stuck inside. You know, this is like a dead tree stuck off the side. But this is the kind of data that, you know, that you just process with the kind of computers you've got. And of course, that allows you to then start thinking of multi-sensor fusion, right? So these are, you know, real problem domains that you can use. You know, LiDAR is a three-dimensional thing. It's a laser ranger. And so is this ground-penetrating radar, this one that produces the point cloud. But you got all this other stuff, too. You know, looking at the same spot in the ground, trying to get some information from it. And now we can build systems that will process all that together. So, of course, let's not forget about deep nets, because starting about two or 3 years ago, when we had our group meetings, you know, where we would call on the telephone and all the different contractors would be talking to the Army, you know, everybody was doing deep CNNs. You know, it's kind of like, oh yeah, well, we'll just dump the data into a CNN. It's an image thing. You know? Or recurrent nets, because it is a time varying problem. Right? So you got a lot of LSTM things going on. So, you know, now, of course, as a matter of fact, we saw, I don't know how many of the 22 posters that we looked at yesterday, you know, were deep nets. I mean, bunches of them. Right? So, you know, it's like, it's the technology now. Right? You can just get it and use it. And of course, I always have to say this because, you know, most of the techniques, the basis of those techniques were back in the late 1980s and the 1990s. And it's just now that we've got big computers, good computers, fast computers, big memories, right? Lots of big data sets that we can make this giant leap, right, in the capability. Okay, so now soft computing. Man, check the shirts out on this one. Okay, so this is going to be my little tutorial part of this, you know, because I asked Pablo Trace if I should have some background information, and he said, oh, absolutely, absolutely. So you know, a lot of people think because the numbers are between 0 and 1, fuzzy memberships or possibilities, and typicalities, that aren't they just really probability? You know, aren't you just measuring probability and calling it something different, right? And so I have a few slides, but one of them came directly from Jim. But this one, my belief is that probability measures whether something is going to happen. What's a probability that, I made this slide when I was in Australia, in Melbourne, and there's a place called Pub Mahoney's. It's an Irish pub. Right? And so they had the pub's pie you could buy. And so you could say there's a 50% chance I had a pub's pie with a pint for dinner. Whereas fuzziness measures how much something is going to happen. So you would say, I ate half of a pub's pie, which is unlikely for me, but I ate half of a pub's pie with a pint for dinner. Right? And so the number is the same, 0.5. Right? It's a number between 0 and 1, but the semantics are completely different. Right? Because if you ask me, did I have a pub's pie, in the first case, for dinner last night, I have to either say yes or no. Right? And once you run the experiment with probabilities, there is no more uncertainty because the event either happened or it didn't. And the probability was only measuring whether you believe, how much you believe it's likely to have happened. Right? So that's kind of the difference, in my opinion, between fuzzy sets and probability is that they're measuring essentially different aspects of uncertainty. They're not the same, right? Or this is my adaptation of something Jim did years ago. So you're lost in the outback, dying of thirst, right? So again, this was done in Australia. And so you're out there, you know, you're dying of thirst, and you find 2 bottles containing liquid, okay? And so you want to have a drink, you know, and in fact, that's a good idea. So, which one of these am I going to take? I don't know, I'll take this. No, it was refreshed.
He's not going to know your secrets.
Okay. Right? And so the question is, which one were you going to choose? Right? Which of these 2 bottles would you take the drink out of? And so how would you process that information? So the first one said, so on the bottle there's a label. It says potable. And potable, maybe Claudio, somebody's calling him up to actually tell him what potable means. Potable means drinkable, right? Drinkable water. And it says the probability of being potable is 0.91. Right? So if you like probability theory, right, you'd say, well, that's pretty high probability. Right? But what that means is it could be something really good, right? Or it could be hydrochloric acid, you know, because all it says is that if I ran an experiment, I mean, if you take the frequency interpretation of probability, if I ran an experiment 100 times, 9 out of those 100, you're not going to get a potable drink, right? You're going to get, you know, something in there that you probably don't want to drink at all, right? Whereas if you said the membership in the class of potable liquids is 0.91, assuming that we understand what memberships are, we'll talk about that in a minute. It might taste a little weird, right? Because it's not 100%, but it probably ain't going to kill you, right? That's my opinion, right? So I mean, I know which one I would pick, right? Because I'm less of a gambler, you know, than I am someone who likes certainty factors, right? So here's what fuzzy sets. I don't know, maybe you don't believe it, and that's okay. I mean, there's many people that don't believe in fuzzy sets, and they're very vocal about it, not believing in it. But here's the mathematics behind it. Very simple mathematics behind it. You start out with some subset, some set X. That's your universe set, the set of all numbers, let's say. Right? And so you can specify a set, a crisp set, by either listing out the elements that are in there, right, in the set. You can write down the defining property. Right? This is like from the 4th grade or something where you learn to do this. I think I was a graduate student by the time I figured it out. But you can say, oh, it's a set of all x such that x is an even positive integer less than 10. Okay. And, or you can specify the characteristic function. And we saw this yesterday, if you remember. We saw this yesterday in the crisp partition of a data set. Right? The idea of this membership function. Right? It's either 0 or 1. It's 1 if you're in there, 0 if you're not in there. Right? So fuzzy set theory just says, okay, let's just relax that constraint, make the membership function go from x into the interval 0, 1, and that's where its value of the function is the degree to which you belong to the set. Now, or how much do you satisfy the defining property? So that's the idea of the potable. The membership compatibility is 0.91. It's how much you satisfy that definition of the pure object. So now you know what a membership function is. You've got, if you want a set theory, right? I mean, this is, in a math class sense. You have to have what do you mean by unions, intersections, and complements? Right? Because that defines a set theory. So Zade's original choices were these. He said, well, you get the membership in the union of two fuzzy sets by just taking the biggest membership of either one. Right? And you get it in the intersection by taking the smaller one. Right? Because what's union? It's like, well, it's either in A or B or both. Right? That's a union. Right? So that means whichever one has the bigger membership, that's the one I'm going to say is the union, because it's either A, B, or both. And to be in the intersection, you got to have both, right? You got to have it in A and it's in B. So that if the membership tells you how much it's in A and how much it's in B, then the smaller of those two is how much it's in A and B. Right? And the complement that he picked was just 1 minus the membership in the set. So the membership in the complement. Right? Why did he pick those? Well, I mean, I'm not going to presume that I understand what was in Lockheed's mind in 1965, but essentially, it's because they are the actual definitions that work for what we normally think of as union, intersection, and complement between regular sets, crisp sets. Right? It's the same. These same functions apply if the sets A and B are crisp. Right? Because to be in the intersection, they would both have to be 1. Right? If you're in both sets, you have membership 1. So the value in the intersection is 1. If either one of them is 0, you get 0. Right? So that's why he did it. Okay, but there are many other possibilities. Here's one called the bounded sum. Right? You add instead of maxing. But then, of course, you can't get bigger than 1, so you chop it at 1. Right? So that's why it's bounded. Or this is called a bounded difference. You look at the sum minus 1 for intersection, and you say, well, as long as that doesn't go negative, right, that's the value you're going to pick. Right? And these are sometimes used in fuzzy logic, which we'll get to in a minute. And there's the cool thing is there's an infinite number of ways to create a fuzzy set theory from these functions, right, that define the sets. And it's kind of the good news and the bad news. The good news is there's an infinite number of ways to do this, to build set theory and combine stuff together by unions and intersections, complements. And I always think of it as combining confidence values. So this is a multi-sensor idea, They're all telling you how much this place you're looking at resembles a landmine, right? Or this person fell down. Right? And so now you want to combine them together. But the bad news is there's an infinite number of ways to do it. And as engineers or computer scientists, we have to pick one. And that's always an issue. So of course that's where machine learning comes in. And also, when you create a fuzzy set theory from regular sets, you give up something. Right? You have to give up a couple of the properties that we normally think of as set theory properties, like the law of contradiction and the law of excluded middle. Those things usually are the ones that go away. Okay, so here's some memberships. Right? So this is my membership in old. Yeah, it keeps moving, you know, to the right for me. So the blue thing is old, and then this would be not old. Right? Just, I mean, it's simple thing. So if you want to look at the union, this is old or middle-aged. Right? So middle-aged is this thing, like that. Old was this thing, and the union is just a max at each point. Right? So I mean, the operations are very simple. Right? Now this doesn't semantically make sense, but that's okay. It's just it just functions, right? So I could change. I got lazy and I didn't want to change the example. And so, you know, the and is the intersection, so it's this thing that goes down. I mean, it's the min, right, of these two functions. The one that was originally yellow and the one that was originally blue. So it's this kind of purpley looking thing, is the intersection. Right? But so one of the questions that people always ask is, where do the membership functions come from? You know, the ones that the smug probability people would say, yeah, where do you get those membership functions? And so of course I would argue that you get them in the same place you get probability density functions. You either make them up, right? You learn from data, or you have a model, right? You say, oh, I think the world is Gaussian, so everything is normal, right? Or it's exponential, or it's Laplacian, or you know, whatever, right? But this is one of my favorite membership functions ever, right? So this came from a pediatric nurse, and so when they're trying to figure out how much Tylenol, how much painkiller to give a kid, right? So they have this looks like a slide rule. Right? And they say, move the slide to how much pain you feel today. You know, so it starts off down here, white, narrow, no pain. Right? Up here it's very dark, wide, most pain. And so you tell the kid to slide the thing, how much hurt you are. Or if they're little kids, you say, pick the face you feel like today. Right? This was that 2-year-old that ran over the 5 kids. And this is the front side of these little plastic cards that they have, right? Pick your face, right? And so on the back side, if you look at the back side of this, on the back side of the slide rule thing, there's actually a number that you interpolate from 0 to 10, I mean divide by 10 and you get a membership function, right? So it's essentially measuring the membership in pain. And of course the Tylenol people then have a chart that says, based on that, give this dosage. Right? So they can administer the dosage, and since it's liquid, they can, you know, make it an analog amount to give to the kid. You don't want to overdose them, but you want to give them enough that the pain goes away. Right? And the little guys, these are this is discrete membership function. Right? Because you only got whatever it is, 9 elements in there. And I thought the interesting thing about this, in my opinion, is that they have 2-digit accuracy. Right? You know, I was looking at Sanaz's chart of numbers, and she had these like 8, 9-digit number things, which of course probably aren't real, right? The number. But yeah, why isn't it instead of 0.37? Why isn't it 4.4? I mean, come on. You know, but anyway, that's what they did. But they weren't thinking of this in terms of fuzzy sets, but it is. It's my perfect fuzzy set right here. All right, so now let's look at the applications of that right in here. So this is what, when we first started doing landmine detection, this is what was being produced by the leading company that was building the equipment for the U.S. Army. Right? They were looking down, radar, down in the ground, and so this is the direction of travel, this way. And so this is the width of the road. There's a bunch of antennae pointed straight down, and they would move, right? And so this would scroll past the human. And the human would have to say whether or not to stop and dig, right, for something buried in the ground. So obviously the red areas are things of high radar reflection, right, in there. And so you would be stopping all these places because these are bright red spots, you know, digging it up. And of course, every time you stop, it wastes time, you become exposed, etc. Right? And so we built an algorithm that was based on, actually it was on fuzzy clustering. You know, we built an algorithm and we produced, so this is the original plot, so we embedded it inside their box, you know, that they had inside this vehicle. And we, you know, we produced this kind of output as it's scrolling past, and that actually is the buried object right there. You know, so I mean, we just threw away the false alarms almost completely by just a simple fuzzy set algorithm, just based on some very simple ideas, and you know, and using fuzzy clustering and prototypes and things like that. So, you know, obviously, we believe this is a great thing to look at. This is, by the way, this is the characteristic that you want to find in a buried object with radar. It's these hyperbolas. It's because as you drive over something, you know, you get this return that kind of looks like a hyperbola. When you're right over it, you get the highest value. When you're, you know, off to the side, it's lower, and then it goes up, and then it goes down. Okay, and then we did many things where we validated it with these blind tests. And this black line, this is a receiver operator characteristic curve, right, which measures, there's always a parameter in there that you gotta vary. And based on how good you are, this is the probability of detection versus the number of false alarms per square meter. It's the way we looked at this. And this black line is a fuzzy algorithm, right? You just based on just standard fuzzy sets that turned out to be the very best of all, right, of these things. Because what you want to do is you want to get up to 100% detection with a low false alarm rate. I mean, that's the key. Right? And now we're doing it with the Navy, right? Because they're worried about things buried in the water, right, down on the seafloor. But the problem that they recognized was that things that are buried in the seafloor look different based on what's under, what kind of seafloor you've got. So the environment becomes very important. And so we're using, again, classifiers and clustering algorithms based on fuzzy sets to try to give a soft segmentation of the seafloor, because it's not like all of a sudden you change from flat sand to rocks, right? There's this gradual transition going across there. If you've got an object buried in there, it's going to look different depending on if it's on this side, if it's in the interface area, or if it's on that side. And so the idea is that you can now blend the classifiers that look for specific things directly with that, you know, with this information about the different types of seafloor, as long as you have this gradual membership. Oh, and this, you saw a picture like this yesterday, right? Huh? Remember yesterday? All right, this is our streaming clustering classifier idea. All right, this is data coming from, we obviously can't identify the people, right? So this has become user 3003. But this is the data, and this is this early warning system that we put in there, right? And this is based on the possibilistic C-means, one mean in this particular case. And so we're ready, we're very close, we haven't done it yet, but we're very close to just embedding this into the daily operation inside Tiger Place. Okay? And so we're doing these things. I mean, this is a picture I showed you yesterday where, you know, these are the clusters. This is in retrospect. This is if I had all the data, right? But we're going to put it in live, right? But you can see the different things that are going on. And of course, this is a terrible color. But I didn't put that color in there. I just used this slide from somebody else, my student. And I didn't realize he put this black background on here, which makes, I mean, it's kind of startling looking, but I don't know how good that is. Anyway, this is a multi-year set of data that shows things happening, right? Because we have the electronic health record available to us, you know. So we're able to do the study to give us confidence that when we put it in live, it's likely to work, right? Oh, so how about some fuzzy logic now, right? So this is a former PhD student of mine, Derek, taking a dive for the team. These are the two webcams, you know, and these are the silhouettes extracted. So these are the cameras on the two. I mean, you know, they're $20 cameras or whatever. You know, I mean, they're very cheap, right? But the processing was the heavy-duty stuff. And then we built the three-dimensional voxel person from this. Right? So, I don't know if you were looking at the voxel person, but it changed colors. Right? So now I'm going to tell you how those colors came about because it's part of the fuzzy set, soft computing for decision making. So what is fuzzy logic? So you got rules. Right? So when I started thinking about this, the big, you know, in the Japanese sort of explosion of fuzzy logic back in around 1990-ish time frame, they had this thing called the one-button washing machine. You know, it's for guys, mainly, right? You just take all your clothes and you throw it in there and you just press the button and say go. You don't have to worry about separating or, you know, all that kind of stuff. And so it figures out all the, you know, how dirty the clothes are, what kind of dirt is it, how long should you have the soaking cycle and the wash agitation and all that, you know, and the rinse cycle. And it had simple rules though, right? They look like this. They were written by a person, right? It would say things like if the muddiness is low and the time to saturate is short, then the washing period is short, right? So these are words, right? Computing with words in a sense, right? Or think of balancing a broomstick on your hand. You know, like this, right? What can you measure? You can measure the angle. You want to keep it straight up in the air. You can measure the angle that it's at. You can also measure whether it's moving this way or that way or stable, right, from the last time you measured. Right? So if the angle is positive small and the change in the angle is essentially zero, then the velocity should be negative small. Because if it's more or less stationary, you don't want to push hard. You want to just push a little bit to get it up vertical. Right? Or if, you know, in an image, if the region is long and straight, then, you know, your confidence in that it's a road is high. So this is what a fuzzy controller looks like. Right? You got the plant. You know, here's the plant. You got balancing the broom, right, in this case. Or this is the decision. These are the variables you're going to extract from a classification problem. Right? Usually they're crisp because we have to measure something, right? And it's usually we get a number in here. Might actually have 18 digits, you know, on the number. So these are, and so then you have something they call that Zade called the fuzzification interface. So you turn these crisp things into fuzzy sets. And then you have an inference engine, something that makes a decision, right, that has some knowledge and does some of that. And then it pops out fuzzy sets on the output side. But if you're going to actually control the broomstick, you've got to tell that usually, I mean, think of it as a cart or one of these drones or something. You have to actually give it a signal that's crisp, and so you use the ugliest word in English that you can imagine, you have the defuzzification interface, right? And you just keep that cycle going. But this could also be just a decision. Is the thing a landmine or not? Did grandma fall on the ground or not? Right? And of course, oh, well, women can do it better, right, than men. Wearing high heels, on a tightrope, on the chin, balancing on the chin. This guy can't barely get it, walking. Okay, so what is your knowledge base? It's these propositions. So this is just like regular logic. If you took regular logic classes, it's just like regular logic, except these are words now and not symbols. So we're going to model them by fuzzy sets. So you've got, U is A or U is not A. And then you've got conjunctions. U is A and V is B. Right? So you got two things, like if the angle is small and positive and the change in the angle is 0. Right? That's the conjunction. Disjunction is an or. Right? It's either this or that, or an implication. This is the key one. If U is A, then V is B. Right? That's the one that says then the velocity is negative small. Right? And we got some other junk in there. Right? So we're going to model the propositions by fuzzy sets. They got a fancy name for it, possibility distribution, but it is a fuzzy set. So the idea is that you have a proposition that looks like this. Region is long, and what it does is it induces, there's a fuzzy variable called length, a linguistic variable that you define to be length, and you say its value is long, and long is defined by some fuzzy set. So for conjunction, disjunction, and negation, use your favorite operators. Now you've got an infinite number of them you can choose from, but you have to fix the one you want. Implication is a little more difficult. If you're a classical logic person, you would say, oh, A implies B is logically equivalent. Right? If you build truth tables, everybody know truth tables? Right? Digital logic. You take a digital logic class. A implies B is equivalent to not A or B, logically, in crisp logic. And so if you want to just directly translate it, you would say, okay, I take whatever A is, take the complement of it, right? And I somehow OR it with B, right? So at a point x, y, right, because you've got two variables, point x, y, you just take that, and so you can use max, right? Why not use max? Because that's as good as anything. So you get 1 minus mu sub A, maxed with mu sub B, right, at the two respective points. Or you can use this bounded sum thing, right? This last one, this thing is compatible with multi-valued logic that was studied back in the 1920s and 30s. That is, I guess, Swedish mathematician. But there's many other translation schemes of a rule. Right? That's the idea, is we want to turn a rule into a function. Right? That's the main thing. You just want everything to be a function, because then you can do stuff with it. Right? And here were the two most popular ones back in the 1980s. Something called correlation min, where you just take the min of A and B, or correlation product, where you take the product of them. And now neither of those is actually a translation of not A or B. It's just a function, right? It's a correlation function. Why? Because they were simple and fast. When you had a microprocessor like the Motorola HC11, right, that had very, very limited capabilities, you couldn't do a lot of calculation. So you wanted something that was simple and easy to do, and this is what they did. Right? Okay, so now you've got a rule. If U is A, then V is B, which is like if the angle is small right? Then the velocity is negative small. You know, I've only got one antecedent. We've got to get the multiple antecedents, but and then you've got some other fact, which is not small, right? It might be about pi over 4, right? Because that's what I'm measuring, you know, when I measure the thing. So now I have to make inference. I want to some approximate value for B, and that's called generalized modus ponens, because modus ponens is the logic, crisp logic way to combine a rule and a fact if they match completely. But this is approximate because you don't have to match exactly. You just have to match to some degree. Right? And of course, there are hundreds of ways that people have done this because we all want to write papers and go to conferences and and so there's all sorts of generalizations of modus ponens. Right? And it's interesting to note that if the domains are finite, if you don't have an infinite continuum of values possible, but you only have a finite number of them, like you enumerate the possibilities, then this generalized modus ponens looks like matrix vector multiplication, except you replace the sum in the matrix vector multiplication by a union operator and the product by an intersection. So you can actually implement it with linear algebra. Right? It's kind of an interesting side effect. Okay, so you got a bunch of linguistic variables. You got membership functions to define these things, like this, low, medium, and high, right? That makes some sense somehow. You throw in a bunch of rules, more the merrier, for fuzzy logic, it doesn't matter. So here's some rules. This is about landmine detection. If the GPR strength is medium and the confidence is low and the aspect ratio in the IR is not mine-like, then the overall confidence is low. This is a rule that one of the guys that worked for that company came up with because he said, I've been looking at these things for, every day, for 8 hours a day, and I know that this is true. Right? And here's another one that gives you a rather high confidence. It's got 3 antecedents and then a consequent clause. Right? And this is kind of an example of actual processing that we did one time, where we had a rule that looked like this. If there's a lot of energy, that's the bright red spots, right? There's a lot of energy in here, and the energy is going up, and then it's coming down, right? That's that hyperbola-looking thing. And the going up and coming down are close together, right? And I'm saying it in words because that's easier for people to describe, right? To say it in words. Then the confidence is high. And so there's actually is a mine at every one of these little white tick marks right here, And so how do we do the inference then? Well, we fire all the rules that relate to this thing to some degree, and then you aggregate the answer. And then you defuzzify it to get a numeric value if you like numbers. Right? And so this is kind of what a rule looks like. Here's the GPR strength being whatever, high, or medium, I guess. Here's the confidence being low. Right? Here's the IR aspect ratio being mine-like. Right? And here's the target confidence. Right? So what you do, this is the way it's really done in the hardware, is you take the actual value for the strength and you look at how much it activates each one of these membership functions. What's its value? You take the minimum of all those, and then you chop this guy off at that value. Right? You do the same thing for the next rule. Right, here's a rule. You take the same values, obviously, because you measured them one time. You find the minimum, which is, I guess, this value right here, because it's got that, and that. Chop this one off, and you get this cone-looking thing. Right? So that's the output of the inference engine. The inference engine is just firing each rule to some degree and produces a little fuzzy set on the output. And then you take those outputs and you can add them together, you can max them, you can do a bunch of things. But if you add them together, you get some weird shape like this. And then to get the actual number back, if you look for the centroid of this shape, I mean, pretend like it's a piece of metal, and you want to put your finger where you can balance it, right, so it doesn't tip. And that's the centroid right there. And that's the number that you report back to the plant, right, if you want to do control, for example. So, you know, the more rules you have, the weirder the shape of this thing is, you know, but that's how it works. So, back to the fuzzy activity. So this was Derek. Now take a look at the colors here, right? You know, there's Derek walking along. He's a very distinguished professor now. He probably doesn't fall on the ground anymore. You know, he makes his graduate students fall on the ground. Okay. So, where did those colors come from? Well, we had 24 fuzzy rules that talked about measuring stuff from voxel person and whether you were upright, kind of on the ground, or in between, right? And so the inputs were some numbers that we measured from each frame of voxel person. The outputs were these upright, we called it bending for some reason, I don't know, you know, kind of when you're in between, and on the ground, right? And this, for each frame, these are the outputs of the rules, right? The rule base. So red is the output, defuzzified output for being upright, right? Green is in the middle, and blue is on the ground. So initially, when we're going, it starts out you know, he was upright, right, walking around, right? And then he fell down. You can see as he falls down, the red goes down, the green goes up because he's in between on the way down, and then the blue goes up, right, because that's on the ground. And then this little extra spike, I don't know if you noticed it, but he was kind of rolling around on the ground, kind of pretending like he was trying to get up. Anyway, you know, so we built that, and then from that, this set of graphs, you can build an explainable AI system, the fourth wave of AI, right? Explainability. So we come up with things that say, well, he's upright in the living room for a moderate amount of time, right? Because we're processing this time graph here, and then he's on the ground for a moderate amount of time, right? Here. So at least you can get an explanation associated with it. So then we stuck these rules to look for falls, right? Because this is what every old person fears: falling on the ground and not being able to get up, and having, you know, and laying there for 8 hours because nobody comes to check on them, right? So these were the nurses told us this. So you can see, for example, if you're on the ground and that's high, and it's been a long time that you're on the ground, then it doesn't matter what these other things are, your fall confidence is very high. Now, you could be asleep, but that, you know, if you wanted to sleep on the ground, but we assume that the elders don't sleep on the floor, you know. But here's one that, let's see, here's one here. If you're on the ground, it's high, but the time is only moderate, but the motion is low, that you're on the ground, then you still want to have a high confidence output in this. So this is just a set of rules, right, that the nurses told us, and then we ran a bunch of experiments, and this is that same plot, right? And there were actually 4 falls in here. You know, you had this first one, these are the confidences as we build it up, right? So fall 1 was a heavy-duty fall, right here. None of this got called a fall in here, right? They were doing different things like you know, stretching and walking and kneeling, you know, plugging in the socket down here. You know, and the second one was a heavy fall. Right? The first one was confused, and they only gave us a 0.5 output. And then fall 3 was this longer fall, and the confidence built up over the course of time as the rules were kept firing over and over again. and, you know, and we had these little shark things. Anyway, so how do we collect the data to build these things? Well, we have stunt actors. All right, because you don't want to actually have old people falling down so that you can, you know, get some training data. Not good, right? So we hired some stunt actors, and the nurses taught them how to fall, like an old person, because that's what they do for a living. And then we ran our system on this, and you know, we compared it to hidden mark-off models, which is the way you normally do classified time series. And so we recognized all the falls and only one false alarm in there, and much better than the hidden mark-off models. Of course, I wouldn't show this chart if that wasn't true. Right? And now that's embedded into Tiger Place, right? And so the clinicians get an email that looks something like this. Right? Fall detected, confidence, bunch of parameters, time, and date, and that, and then a link to the video that you can look at, right? Like that. Ooh, that hurts. There's another one there. All right, here's the false alarms. Oh, the dog. Right? And this is a bad one here. This is the sheet. Right? On the ground. Throw the sheet on the ground. Right? It's big, it's on the ground. So this is where the IR is going to come in handy, because this isn't going to look like a human, hopefully. Right? And you know, we do things again using fuzzy clustering. We can capture the gait, and this is what we're doing is we're measuring this as with respect to one of these marker systems, you know, that we validated it with them. So it's a clustering problem. This is grandkids. So I'm going to skip over linguistics, man. We're doing a bunch of stuff because I got this thing, which everybody wants anyway. But we're building lots of linguistic descriptions now, all based on fuzzy rules that we can measure and provide this, because the clinical nurses are really good, but the people that are at these nursing homes have very low education, and they're not quantitative at all. So showing them a graph is not a good thing, right, to make sense out of it themselves. And so, you know, we run this. All right, okay. So I mean, to show them this kind of stuff is not going to help, right? The PhD nurses like this, but there are not too many PhD nurses that are at these nursing homes. So now we have a linguistic alert. You know, we produce an output that looks like that. And we did a bunch of case studies, you know, where, again, this is all retrospective in this particular case, so that we know what the answer was. This was a renal failure that we were able to capture linguistically before it happened. I mean, would have been before it happened. Same thing here. This is a urinary tract infection. You know, you're up and out of bed a lot at night. You know, your bathroom visits are high because you got the motion sensors. You know, so we're able to produce these kinds of linguistic alerts. And now we're able to actually go back and link them to previous medical conditions. You know, so if they had, you know, so this says that previously the pattern that I'm seeing now was associated with fall, aches, pains, and something, weakness, right? Because that was what was recorded in the electronic medical record for some previous time. And so that's the new stuff.
Same person.
Huh?
Same person or other person?
No, same person. We're using only the same people, right? But that's, again, that's a question, is how much population stuff can you really use? We've been focusing too much on, focusing almost primarily on single people. All right, so there's a bunch of fielded systems, you know, that are based on fuzzy sets, and we get commendation, you know, got commendations from the Army in this case. I mean, this thing is actually in Afghanistan, you know, this vehicle. And I've been there for many years looking for stuff buried in the ground. And this is the company that's licensed our elder care software. It's a company called Foresight Healthcare. And this is their sensor now that's got, so it looks a whole lot different than Microsoft Connect. Right? Oop. Yeah. So this is in a hospital room. They had it installed because people fall a lot in hospitals, as it turns out. I didn't realize that, but you fall down a lot. And there's also people that fake it. You know, they say they fell, and they try to sue the hospital. You know, but this guy did fall, as you see, right, as he was trying to get into bed. But it's kind of a double duty thing for that. Yeah, okay, enough. Okay, so conclusions, good. So yeah, Blackfeet was happy, right? Having a glass of something. Okay, my opinion, he hit it on the head, right? When he proposed this idea of recognition technology, explosion of new sensors, computing power, visualization tools are so much better, great signal processing, and of course soft computing for decision making, to manage the uncertainty, right, that's in the process. So that's all for me. And so when you end a talk, you should always thank your friends, right? And who are my friends? Well, these are the people who give us money. So of course they have to be my friends. And of course I thank all of you for putting up with me today. So,
Okay, thank you very much for this very nice talk. And we have time for a few questions, unless you all want to go for lunch, and then we are not going to have any questions. Did you raise your hand? No, you did.
no, nobody. Oh, there. Pablo Dos.
Pablo Dos?
See,
You are hiding here.
he wants to be warm, sitting by the fireplace, right?
It's a simple question, maybe stupid, because I don't know much about fuzzy sets, but sometimes you get the data and it's easier to train a neural network.
Yes.
Which is a total useless black box in terms of explainability.
But yeah, it's in terms of
But fuzzy sets are not.
Right.
Is there a tool you can use to fuzzify, obtain the rules out of a neural network?
Okay, that's a good question. I think the answer for if it's deep CNN, no. If it's Raghu Krishnapuram and I worked a lot on these things we call fuzzy aggregation networks, where the nodes actually perform fuzzy operators. And you would train it, and after you were done, you could look and say, oh, there's a disjunction. So that doesn't mean it's this or that, you know, or it's a conjunction, or it's a mean, or whatever. But I think in general, I mean, the best we've been able to do so far is to run 16 models of deep networks, which of course you can easily download off of GitHub, right? And then fuse the results and build an explainable fusion, right? So you could say, oh, we're confident here because these three are very strong in their belief in the class label of this, and these are medium, you know. And if I threw these away, I would still get a high confidence, you know, kind of thing like that. So, but it doesn't explain what the neural net's learning at all. I don't know of any way to do it, you know. Now, what a lot of people have done is they've taken their favorite deep CNN and they go up to the feet where you flatten the feature layer out and then strip off the multi-layer perceptron at the top and put a fuzzy rule base on top of that. So you use the CNN to be a feature extractor, essentially. And then you feed the features into some other decision tool. But the trouble with that is that, at least in most of these, the dimensionality of the feature vector is gigantic. It's like, 9,000 or something, So then you have to run it into some series of auto-encoder things to shrink it down, so, because this stuff doesn't work if you have 25 antecedents. It's not explainable anymore, right? Having 3 antecedents, 4 maybe, you can sort of say, yeah, this is the explanation. But if you have 25, it's a black box, my opinion.
Any other question? I have a question regarding, you said that people that were guardians or whatever at the elderly people home, it was difficult to interact with them because they were not very qualified. So
yes.
How did you test your reports to make sure that they would understand the right thing?
That's a good question. So my colleague Mihail Popescu has an NIH grant, the National Institutes of Health grant, and it's exactly this question, is do the linguistic summaries actually provide more information, or are they better than the other one? And the things we can measure is how many clicks the staff click on the alert. So we have the standard numeric alert that you can click on there and it sends you to that web page with all the graphs and stuff, right? And then you have to figure out what to do, right? Or you have the alert that comes in and it's just this set of text things. It says, oh, last night, the heart rate was high. And over the last 2 weeks, that the blood pressure has been increasing, things like that. And so we're measuring, we're still at the end of that grant, but we're measuring the amount of interaction of the staff with these 2 different approaches, the standard one, the one that we've got in place, and this new one.
But it's always better than just giving an instruction like call the doctor immediately or call the doctor if it is repeats or something like that.
Yeah, you can't do that because you can't make medical decisions. Okay. See, saying call the doctor, if we do it automatically, that's a medical decision. Okay. And so then we're liable. Actually, the machine is liable. So it's this ethics thing that Sanaz was talking about. There's a big ethical question as to what do you do with this information? And the best we've been able to do so far is to say, it's really not, we're not going to make a decision, we're going to provide information for the humans to make their informed decision.
But it's more or less the same as in the autonomous driving cars, that probably they have less accidents, but the question is when they have, who's responsible? Right. Here would be probably the answer. Yeah.
And this is our doctors said. Yeah. We don't want you being the doctor. We want you to provide information for us so that we can do our job better.
Okay, any other questions? Yeah.
Oh, hey, a real question.
The question is, if the data you're obtaining from your sensors are compared with the information that the nurses or the physicians write into the medical records.
Yes, that's it. Right. So that's at the very end. We're now linking the medical record right to the data. So the electronic medical record that is being created for each person at the facility. So it is, it's in the early stages of that linking, because this is all in text, right? Somebody just typing, right? And of course we got the sensor stuff. So now we're trying to say, what this condition that we saw 2 months ago, do we see a pattern that's like that? right? And then we put it in the alert. It was the sort of the. That's the trouble with doing animations, is you end up with this kind of stuff. Where was that at? I thought it was right there. Oh, there. You can't read it though, I realize now. But that was on purpose, you know, I didn't want you to actually have to read. You know, but that's what this little box says. Previously, when we saw this set of patterns, it was related to either a fall or weakness or pain. So that's from the medical record in the past.
Thank you. Any other questions? Okay, then we will meet this afternoon for our last plenary session, and let's be back at 2 p.m. Thank you very much.